2018 में जब मैं एक कॉन्फ्रेंस में गया था, और वो कॉन्फ्रेंस थी वन डे वर्कशॉप ऑन द लाइफ और एंड वर्क ऑफ प्रोफेसर मेघनाथ साहा एंड प्रोफेसर एस एन बोस। तो उस वर्कशॉप में मैंने काफ़ी सारी चीज़ें सीखी थी, काफ़ी सारी चीज़ें जो है वो पता करी थी, और मैंने एक पोस्टर भी प्रेजेंट किया था मेघनाथ साहा सर पर। उस वर्कशॉप में, उस सेमिनार में मैं एक ऐसे व्यक्तित्व से मिला था, एक ऐसे साइंटिस्ट से मिला था जो कि जिनका प्रभाव जो है मुझ पर बहुत ज्यादा है। और मतलब मैं हमेशा से चाहता था कि उनको अपने इंटरव्यू पे बुलाऊं और उनके साथ एक इंटरव्यू करूं। और आज फाइनली आई हैव हिम ऑन माय पॉडकास्ट, एंड आई एम रियली हैप्पी टू हैव हिम ऑन माय पॉडकास्ट। एंड let me just introduce you to Professor Partha Ghose. Partha sir, very welcome to Rozender Talks. So, sir, it's been an honor to have you. And let's just start with the part one of the of our interview, which is your research is in light. You have done a lot of research in light. Please tell us something about your research in that area.
Uh, Light has always been absolutely fascinating to me because light is what reveals this whole world to us, the beauty of the world, the majesty of the world. And so, not so much by planning, but it so happens that a lot of my work, particularly since 1989, has been mostly on light. Before that, I used to do particle physics, quantum field theory, and so on. So, one of the first things that I did about light was to show the nature of its nature. Is it a wave or is it a particle? And I did that work in collaboration with Professor Dipankar Home and Professor Girish Agarwal. And we used an experiment which was used first by Sir J.C. Bose to show that the millimeter or sub-millimeter waves which he had generated in his lab, which he had detected, were waves rather than particles. So he had a double prism and whose distance could be varied. And he had two detectors. One detector would detect the radiation reflected by the first prism. The other detector would detect whatever it goes through the two prisms. As he varied the gap between the two prisms, he saw some evidence that the so-called radiation which he had produced in the lab was really wave-like rather than particle-like. The reason was that as the gap increased, the reflection increased, and as the gap closed, the transmission increased, and that is what Maxwell's theory predicts. And he saw that, and so that was one very important experiment. What we try to do is to see what would happen if instead of sub-millimeter waves, we send single photons at a time. And we worked out from quantum theory that this double prism would act like what is called beam splitter. And because single photons are indivisible, they are quanta of light, they cannot be divided. So it will be either reflected or transmitted. Now, we also suggested that there should be an anti-coincidence circuit so that to check whether you are seeing reflection and transmission at the same time, or you are seeing either reflection or transmission. quantum theory predicts that you should see either reflection or transmission. And that's what Japanese group of physicists, Hamamatsu Photonics, they did the experiment and they found that was indeed true. But as the gas slows down, you could see more and more photons being transmitted. Now, if they are transmitted, if one photon is transmitted, it's not reflected. So that shows that it is a particle. But according to our concept of a particle cannot tunnel through a gap. Only waves can tunnel through a gap. And therefore, the conclusion was that whatever was going through and transmitted was acting both like a particle and a wave. So that was quite unexpected from Bohr's complementarity principle, which says that you can either see the particle or the wave. So this created a star, and a lot of work has been done on this. So that was one thing that we did. Then I also got interested in entanglement. Entanglement is something which is very specifically, or which was thought to be very specifically quantum. And it arises from the fact that in quantum theory you have this superposition principle, that you can superpose two states, quantum states, to produce a third state. Now you cannot add two particles to get a third particle. That just doesn't make sense. So that is the difference between Newtonian mechanics and quantum theory, which says that strange things like superposition can happen. Then once superposition happens, you see interference effects, and also what is called entanglement. That is, distant particles can interact, go apart large distances, but still some correlation will remain, which is purely quantum. So if you do something to one object, the other object will get affected instantaneously. So this was the famous EPR paradox, and Einstein thought that this was something very odd. It shouldn't happen. If you believe that there is this, the world is independent of observation, it's something real there, and also that it is local, which means there cannot be instantaneous action at a distance. If you assume these two, then this prediction of quantum mechanics is odd. So there is something incomplete in quantum. Now, it had occurred to me quite early that all you need for entanglement is the superposition principle. Now, this principle is valid also for classical optics, classical light that we see. We see interference. The famous double slit experiment of Young, or
Yes,
Young's double slit experiment, shows interference. So there is interference. And if there is interference, what is common between quantum interference and classical interference? My hunch was that classical light should also show entanglement. And this has turned out to be true. A lot of people have worked on it, and they've done experiments. They've shown that what we call classical light also shows entanglement. Now, the question, of course, is there a difference between quantum entanglement and classical entanglement? All those questions are being studied by scientists. But the fact remains that something is totally new in this, that classical physics also can have entanglement. This was not known. Schrödinger, in fact, had said that entanglement is purely quantum. Now, this is, I think, because when people think of classical physics,
actually,
yes,
sir, I'm not getting the classical entanglement part. because in quantum mechanics I have discussed about the entanglement with a few people earlier, but quantum entanglement is something which we can like understand, or something we can get into our brain. But please explain something about the classical entanglement, because I'm not getting the classical entanglement part.
See, when you say you understand quantum entanglement, I seriously question your understanding.
Okay.
Nobody understands what is quantum. That is the most mysterious thing. Now,
Yes,
what
sir.
is entanglement basically? Let us understand that. But if you have a state, you have two systems, and each is described by a vector in a Hilbert space. That is what quantum mechanics does. Then you can write a state of these two particles, which is not factorizable or separable into a state of one particle and a state of another particle. When you can write a state which is the product of two states, then those two particles are statistically independent. But if you can't write that, and in quantum mechanics, you can show that there inevitably will be states which are not factorizable, then of course there will be these correlations. And this non-factorizability is called entanglement. Now, since the states in classical optics are also states in Hilbert space, there's a very general theorem, mathematical theorem, which says whenever that happens, you will have entanglement. That is, there will be states which are not factorizable. I'll give you an example. Let's take unpolarized light, and let us pass it to a prism which separates different states of polarization. For example, if you pass light through this some special kinds of prisms, then unpolarized light enters and two different rays come out. One polarized horizontally and another polarized vertically. This is called ordinary ray and extraordinary. Now, therefore, you have produced a state. We have produced a state in which, in one part, it is vertically polarized, in the other part is horizontally polarized. And this is a non-factorizable state. You cannot write it as a beam of polarized, vertically polarized light times a beam of horizontally polarized light. You can't write it. So this is actually mathematically the same as entanglement. So such entanglement can happen in classical physics, classical optics also. It cannot happen in particle mechanics of the Newtonian type, because particles are not represented as vectors in a Hilbert space. But in classical physics, or rather a very important part of classical physics, is electrodynamics, light, which is so different from ordinary particles. And the light has this common property with quantum mechanics, that the states are represented as vectors in a Hilbert space. And that makes all the difference.
Oh, oh. Sir, from your first explanation, I would like to uh, re-ask the question that you said that you sent one photon at a time to study whether it is transmitting or it is reflecting. So, first of all, how did you manage to send one photon at a time? And secondly, how did the dual nature came? Like, how did it came when it is once reflecting, or what were the conditions that that made you to realize that okay, this is like acting as both particle and a wave? And another question, what if I blast a photon, like I hit a photon with something? What if I hit a photon with something? Three questions I have asked. One,
No,
please.
let us go one by one. Otherwise,
Yeah,
I'll
yeah,
forget.
yeah, yeah, yeah.
Let's go one by one.
Yeah. Okay. So
First,
first,
double
for,
prism experiment.
how one single photon
In the double
goes.
prism experiment, we did a theoretical analysis. That if we could send somehow single photons, what would happen? What would quantum theory say? So that was our theoretical understanding. Now our arguments were so solid that experimenters immediately became interested. And as I said, a group at Hamamatsu Photonics, Japan, they took up this challenge and they did the experiment. We didn't do the experiment. They did the experiment to see whether our predictions were right. And they could produce single photons at a time by what is called parametric down conversion of laser light. This happens when you use nonlinear crystals and so on. I don't want to go into those details, but it is possible nowadays to produce single photons. So they did, and they found that our predictions were correct.
Okay. And the next
What is the
question
next
was,
question?
how did you predicted the dual nature when the light was once reflecting and other time it was transmitting? So how dual nature came?
Yeah. Okay. The dual nature of light has been there with particle duality since 1905. It's something very, very difficult to understand. So Niels Bohr had come up with its principle of complementarity, in which he mentioned that in a typical interference type of experiment, you will either see the interference pattern or you will see particle-like transmission. You cannot see both at the same time. So this was a resolution that, which is very new in quantum mechanics. So the quantum reality is different from what we imagine reality to be. Quantum reality is so nuanced, so deep, that just by doing one set of experiments, like say interference, you cannot get its whole nature. You have to do the other type of experiment. The two put together would give you a more complete picture. That is the picture of complementarity. So according to Niels Bohr, that is how quantum reality is. And this is the only way to understand. Which means in a way you are giving up what is called two-valued logic. Right, wrong, yes, no. No, it's the quantum world is not like that. And to get a scientific view of it, he enunciated the principle that the two are mutually exclusive. You either see this or the other, never the two together. But in this double split prism experiment, as I explained, a photon which is transmitted has to leap through the gap and therefore must behave like a wave. No particle can leap through the gap. But the very fact that that particle is not at the same time reflected, shows that it is behaving like a particle. It is behaving both like a particle and a wave. So, in some way or the other, it seems, I mean, this is debatable, that Niels Bohr's way of enunciating this problem of complementarity is not fully clear. Let me put it that. So that is why people have done more work on it. They have used quantum information theory to understand it. Because after all, whenever you do something, you gather information. So if you use information science, then you can formulate this problem little more clearly than Niels Bohr could do. So that's the upshot of our proposed experiment.
And other question was that what if I hit a photon with something like another photon or something, like I just want to blast the photon. Can it happen, or is there anything which can be explained around it?
According to quantum theory, it cannot happen because by hypothesis, the photon is indivisible. It's the quantum, it's the basic minimum amount of energy which light of a particular frequency can have. E equals h times nu, which nu being the frequency. Once the
Frequency.
color of light, the frequency is fixed, its energy is fixed, and that is the minimum. You just can't make it any less. So photon cannot be blasted, as you were saying. And the other thing is, two photons do not interact directly. Light can pass through each other. Two beams can pass through without influencing. So you cannot see light by using light. Of course, scattering of light by light can happen, but that's in some higher order quantum processes. But you can hit a photon by something else, like an electron. You'll have electrons scattering off a photon. That happens all the time.
Oh, oh, okay. So, sir, Bohmian trajectories and de Broglie-Bohm theory. Uh, Please explain the de Broglie-Bohm theory, and what was your work in calculating the Bohmian trajectories of the photon, and please also explain what is the Bohmian trajectories.
Okay. So the de Broglie-Bohm theory is an interpretation of quantum mechanics where you add something to quantum mechanics, which is, let me go back. In quantum mechanics, you have this principle that you cannot, there is no precisely defined trajectory of a particle. Whenever you observe a trajectory, it always has a width, like the tracks in a bubble chamber. They have a width. They are not infinitely thin. So ideal trajectories of particles do not exist because Heisenberg's uncertainty principle rules that out. But that's a very strange thing. So what de Broglie and Bohm did was to introduce an extra condition in the theory to define a trajectory, which is called the Bohmian trajectory. However, this trajectory, they at the same time postulate that it is hidden. You can never observe it. But with its help, you can understand many things more intuitively than you can do in quantum mechanics. So that is the idea of a Bohmian trajectory. You can calculate by using that extra condition, which is called the guidance condition. You can actually define the momentum of the particle. Once you have the momentum of the particle, then you can get its velocity, and you can also integrate it to get the position of the particle as a function of time, which is the trajectory. And this is the Bohmian trajectory. You can calculate. Now, Bohmian theory was initially developed for non-relativistic quantum mechanics. But when you talk about light, it is essentially a relativistic system. So the question was whether you could at all define consistently the trajectory of a photon. Now, I don't want to go into the technical details, but we had a way of showing how to calculate that. And I and my student colleagues, we calculated those Bohmian trajectories for several cases. and this was published in Physics Letters. And later on, much later, Ephraim Steinberg and his group, they claimed that they had actually observed those trajectories exactly as we have predicted by making use of what are called weak measurements. Now let's not get into all the technical details, but what they determined was an average trajectory, not individual trajectory. So again, there are people who doubt it and so on, but this goes on in the frontier of physics anyway. That's how physics advances.
Okay, so sir, this was the physics part, and apart from the physics, you have done research in Indian philosophy too. So, how did you use like Mukundakya Upanishad and Nagarjuna's in your research, and most importantly, the mathematical modeling of cognition?
Well, I have always been interested in philosophy generally because I find that you actually do not understand anything at all unless you view it from some philosophical point of view. That is true of everything in life, and that is also true of physics. Einstein himself used these philosophical insights to understand why Newtonian mechanics was not the final word, why you required special theory of relativity and then general theory of relativity. In his Brownian work, Motion also, he was deeply inspired by philosophical ideas. That in physics, you cannot have just postulate, atoms and molecules had never been observed before. So some philosophers, they were positivists. They said that you cannot see something, then you should use it in physics. So Einstein was convinced that these things existed. So he used the Brownian motion to show that those jiggling motion in Brownian motion is actually caused by bombardment of atoms and molecules. And exactly calculated how would be the distance, how would the distance as a function of time, what would be the nature, how would X vary with time. And he predicted that, and as you all know, that was actually observed experimentally through all the great contributions of Einstein to actually prove that atoms and molecules were real. They are there, not just hypothetical. So deep philosophical ideas are very important. And I have always tried to understand the philosophical background because that immediately clarifies a lot of things. That's how I became interested in philosophy and the philosophy of science. And I used to work with a philosopher, a Marxist philosopher, Dr. Devi Prasad Chakrabarty. He had written a famous book called Lokayat. It's about the empiricist tradition in ancient India. He had a scheme from the Department of Science and Technology to write some 3 volumes on the history of science and technology in ancient India. And those volumes have been published. I was one of his consultants. So I learned a lot of philosophy through that process. And in that process, he had introduced me to a particular type of Jain philosophy called Shyalvada. I don't want to go into that. It's a fascinating thing. And then eventually, the younger Devi Prasad Chakrabarty, also philosopher, ex-professor of Jadavpur University, he was also a minister in Indira Gandhi's, commerce minister in Indira Gandhi's cabinet, became a governor of Punjab. After retirement, he also got he used a lot of money to write volumes on various aspects of Indian philosophy. Now, he had asked me to edit one of these volumes, which was on materialism and immaterialism, Indian philosophy and the vistas. That is when I really started reading philosophy, both Indian and Western, with the help of a lot of friends. And that volume was published. It's nearly 1,000 pages. And there, of course, Buddhist philosophy was also covered. Nagarjuna's work was also covered. And then I found, I was trying to understand this problem in quantum mechanics called measurement problem. And there's no solution to it. There are hundreds of different interpretations of quantum mechanics to try to explain this in some way or the other. But there's no consensus. So I thought maybe Buddhist philosophy might help, because Buddhist philosophy is doesn't have any God in it. It's very rational. And I started studying Buddhist philosophy with the help of some friends. We organized courses in the old Nalanda University. And so I was introduced to the basics of that. And through my introduction, then what happened was I was also asked to give a series of lectures to Buddhist scholars in Sarnath. They have in Sarnath a university. Now it's called the Central University for Higher Tibetan Studies. And their Vice Chancellor, Professor Samten, and I became very good friends. And he had asked me to go and talk to the Buddhist scholars about science. So while I spoke to them, I also learned a lot. So that's how I came to study Nagarjuna. I'm absolutely fascinated.
How much science you have find in the Indian philosophy, and what do you think about? Is it all how much science you have found in the Indian philosophy, and what do you think about its non-existence in today's world? Like many of us, who are science students, kind of think that Indian philosophy don't have any scientific sense, because what we have taught is philosophy and science are two different aspects. What we have taught. So please tell something about this.
Well, let me say this. In old days, both in Europe and in India, science was called natural philosophy.
Science was called?
So it was a philosophy, natural philosophy.
Okay.
Newton's book is called Principles of Natural Philosophy. It's famous Principia.
Yeah, Principia Mathematica.
Some departments in England, for example, physics departments, they were known as departments of natural philosophy. That's the philosophy of nature. Now, eventually, when science got broken up into various separate disciplines, and people started concentrating on single disciplines, they lost this overall vision. So science became science, and people said, oh, philosophy is something that we don't need to bother with. It's a waste of time. Your job is to observe, calculate, and see what do you get. Very pragmatic approach. Now, in India, that never happened because modern science discovered in Europe, that is the science, you can say Galileo onwards, Galileo, Newton, and so on. When that was happening, India was in a bad shape. So that sort of thing didn't happen here. However, if you look at Indian philosophy as such, as would be judged to be philosophy by Western scholars, then it's philosophy with science, except that it's trying to understand science, what it means. That is philosophy. Actually doing science is different. If you look at science that was there in the old philosophy, that can be separated out into science proper, like the work of Aryabhata and the various astronomers and the mathematics that was developed. All that is very much there. It's not called philosophy. It's called Indian science. So it's a way of playing with words. But definitely, astronomy is an empirical science. So, I mean, old Sanskrit literature is full of astronomy, full of mathematics and all that. So all that is there. We don't call it philosophy. We call it science.
Oh, oh, okay. So, sir,
Lot of deep mathematics was discovered hundreds of years before they were rediscovered in Europe. Even the principle of Galilean relativity was clearly enunciated by Aryabhata. Clearly. But what has happened is, after the scientific revolution in Europe, because of the expanding colonial activities, they always wanted to see everything from the European point. And they just poo-pooed anything else that happened elsewhere. That's how we have our education system was designed by the colonials. And we were never taught all these things. But gradually there is an interest now in rediscovering our past. And that's, I think, a very good thing. Of course, you mustn't overclaim things. That is, I think that would do injustice to our old science. We have to focus on the real good science and mathematics that was done long ago here, like the Fibonacci sequence. I mean, now there's no doubt. There's no doubt the zero was invented. And enormous amount of mathematical work was done by the Kerala group of Kerala mathematicians. So all that is being rediscovered now. And hopefully these will be taught someday in schools and colleges. That depends on our government and our education policy.
Okay. So, sir, everybody knows one name, which is Einstein, and many Indians. How can we forget the name of Sri Rabindranath Tagore? So both of these personalities have a conversation with each other, and not many people know the conversation between them. You have wrote articles and books on these things. Please tell us about what was the level of conversation in between these two personalities.
Well, they met several times. I think the first meeting happened in 1926, perhaps. But then in 1930, they met twice at Einstein's invitation. Tagore had just given his famous Hibbert lectures in Oxford, which was later published as The Religion of Man. where he put man at the center of everything. And he talked about the divinity of man and the humanity of God. So man is at the center of everything. Now, in quantum physics, to which Einstein had contributed greatly, the role of the observer became very important after Heisenberg's uncertainty principle and after quantum mechanics as we know it today, based on Schrödinger equation and its probabilistic interpretation of the wave function. It's the observer which kind of creates phenomena. If there is no observer, there's nothing. Einstein was very disturbed by this. He didn't believe it. And at that time, he was very worried. He was having a long debate with Niels Bohr. All that is recorded on this question. And Bohr was taking the point of view that the observer is necessary. And Einstein believed in a world of reality which is independent of the observer, independent of human thinking. There's something out there. Our job is to think and understand it. That was Einstein's idea. So he invited Tagore, whom he respected immensely, for various other reasons. They had collaborated on various other aspects, on peace and so on. He wanted, the first question he asked him was whether he believed in a reality which is independent of the human entity or not. And of course, Tagore said, no. So the whole conversation was on the nature of reality. Is it independent of the human entity or is it dependent of it? It's a long conversation in which the two were giving their respective opinions without quarreling, without any rancor, but basically trying to stick to their positions. It's absolutely fascinating how Tagore was not using any quantum mechanical idea at all. He was speaking from general philosophy, his general perception. He was steeped in the Upanishadic tradition. But he was, in my opinion, a dualist. I can prove that. I mean, he has himself said it. This world is essentially dual. And it's the Vaishnavic idea of Radha and Krishna, of the individual soul and the universal soul. And the relationship is one of identity, eventually. So it's called the, Sri Chaitanya had enunciated this philosophy of achintya veda bhed. There is bhed, there is abhed. It's achintya. You cannot rationally, mathematically, philosophically understand. It's something that you have to realize. And Tagore was steeped in this. And he believed that all the color, sound, and everything that we see or hear, they are essentially created by the human body and mind. There is something out there. But what it is, we can never know. We can only know what we see, what we observe. And so that was the debate. Fascinating. I mean, Tagore's point of view was very much closer to the quantum physicists than to Einstein's. That's why these days, a lot of quantum physicists refer to this. That here is the great Indian sage saying something that we have also been saying as a kind of justification from a philosophical point of view. In 1929, shortly after Heisenberg had done his famous work, he came to India He was actually going to Japan. So came to India first to see Benares and then came to Calcutta to see Tagore unannounced. He was detected by some students in the library of the famous science college in Calcutta. They saw a Sahib sitting there and they were curious. They found him collecting some manuscript. The author of the manuscript was Werner Heisenberg. So they knew that this was Heisenberg himself sitting there. So they ran to the head of the department, Professor D.M. Bose. So they all came running. All this is recorded by D.M. Bose. And they took him to Farpo's for lunch. Farpo was a famous restaurant in Kolkata, overlooking the Maidan on the first floor. So they gave him good lunch. And he then said, I have come to meet, is it possible to see the great poet? I want to meet him. Fortunately, Tagore was present in Kolkata. So D.M. Bose knew the poet's son, Satyendranath Bose, and they fixed up a meeting between them. So they went, they had a fine tea, and then Heisenberg went in to see Tagore. Unfortunately, nobody else went, so there's no record of what was discussed. But according to D.M. Bose, when he came out, they asked him what happened, what did you think of it, your conversation. So what is recorded is, he says that, he reminded me of one of the great sages of ancient India. Then I wrote to Heisenberg's student, Rechenberg, who with Jagdish Mehra had written this famous series of books on the history of quantum mechanics. So I asked him whether he knew about this visit, whether he could tell us what was discovered and discussed. And he wrote back to me and sent me the Xerox copy of a postcard. Actually, after the meeting with Tagore, Heisenberg had gone to Darjeeling, from where he sent this letter to his father, saying, you would recall this great poet who came to Munich. I went to see him. But in that letter, he says that he was explaining to me or talking to me about his new school that new university he was setting up in Shantiniketan. But Heisenberg's comment was that I doubt whether the British would allow him to do it. But there was no mention of anything else. But Fridtjof Capra, who wrote The Tao of Physics, has written another book called Uncommon Wisdom, in which is based on various interviews he had with great physicists, including Heisenberg. And there he says that Heisenberg told him about this meeting with Tagore, that he had gone there specifically to meet him because he was very worried about the meaning of the new physics. And according to this book of Capra, Heisenberg said that Tagore explained everything from the point of view of Eastern philosophy so clearly that I came out completely satisfied. So this was the depth of understanding of this poet. He was not only a great poet, a great thinker, great seer, great visionary, etc., etc. So I am full of him. So I think all these things should be known. Then he went to Russia from there, and Einstein's daughter accompanied him. After coming back from Russia, he had another meeting with Einstein in common friend's home, Dr. Mendel, who is a geneticist. And there they discussed a lot of things about Indian music, Western music, the differences and so on. Fascinating.
Yeah. So it was beautiful listening to the stories of Sir Rabindranath Tagore. and it would be great if I could be there and just have a few more things to share with you. But I'll come to Kolkata and we'll meet you soon.